Welcome back to Physics with Ben. This is a continuation of the video series on Hooke's Law Experiment 1. We are done with the first experiment and this is the graph for that particular experiment. You may love to click in the description box below to find all the videos on Hooke's Law, the theory for Hooke's Law, the calculations for Hooke's Law, and then also the video link for this particular experiment we're about to plot the graph. You may also love to turn on the notification bell so that anytime I upload a new content, you'll be duly notified. Also subscribe, like, and comment, and promote Physics with Ben in your own little way. God bless you. So without wasting much time, we are asked to plot. If you have watched the other video, you will not be confused. So if you have not, you're just coming in, go back and watch that video. You can find the link in the description box on this video you are watching currently. So we are asked to plot the graph of E on the vertical axis and M on the horizontal axis. That is what we are going to do right now. So the graph of E on the vertical, that is this column on Y, and M on the horizontal axis. So what we are going to do here first is to find the scale of the graph. The highest value here is 3, while the lowest value here is 6. So we can choose a scale. This is a WAEC standard graph. Going this way, we want to leave this line. We want to leave this line down. So we say that from here to here, this is 2 cm. 2 cm to represent 1 unit. Will it go? Let's try and see. This is 1, 2, 3, 4, 5, 6. Our graph will shrink. Let's check for 4 cm. This is 1, 2, 3, 4, 5. That will not go. So with that, we will shift our graph somewhere here. So this is 1, 2, 3, 4, 5, 6. So with that, we have covered a good percentage of our graph. So we'll draw this straight line here. This is our horizontal line. Good. And then the horizontal axis, the highest value is 150, while the lowest value is 70. Highest 150, lowest 70. So can we say that 2 cm to 100, 2 cm to 50 units? Let's try and see. This is 50, this is 100, and this is 150. Oh, let's say 4 cm. This is 50, this is 100, this is 150. That will make the graph to be too small. Let's look at 4 cm. Can we say 4 cm to 100? This is 100. This is 200. Oh. 10. So we're gonna choose 2 cm to represent 20 units. So this is 20, 40, 60, 20, 40, 60, and 160. So this is what we have here. Good. So we are free to draw our line now. We can draw it from here straight down. So this is 0, 0. And then up here is the graph of m on the vertical axis. So this is our m in grams, and then extension in cm, and this is 1, 2, 3, 4, 5, 6, 7. So the next thing we are going to do is to find the value for each small box. So for this we have 1 divided by 10, 1 divided by 10. The value for each small box here is 1 divided by 10, and that is 0.1. Good. So the value for each small box on this wing is 20 by 10. That's 2. 20 by 10. The value for each small box here is 20 divided by 10, and that is 2. Good. The next thing is to plot our graph. So when the force was 70 gram, the extension was 3. How do we plot that? Where is 70 gram? This is 60. 70 is halfway. How do we locate 70? Let's count. This is 1, 2, 3, 4, 5. This is 70. 70 is right here. So we trace this point and it will hit 3. We trace this point here. It will hit 3 here. I did not predict today's graph as I've been doing as usual, but always remember that anytime you have an increased trend, you must have graph of this nature. I always predict graph in all my videos. That is my signature. So this is the first graph you may have, the second graph passing through the origin, or the third graph. This graph is a graph that looks like this. Y is equal to mx plus c. And the second graph is a graph of y is equal to mx, having no intercepts. And then the third graph is the y is equal to mx plus negative c. So any of this graph is a graph we're going to have. But if this experiment actually obeyed Hooke's law, we are going to have the second graph or the first graph. The first graph or the second graph, even the third one. So let's see which one we're going to have at the end of the day. We are done plotting the first point. We are done with this point. The second point is 3.8. Where do we locate 3.8? 3.8 somewhere here. How do we locate it? Very simple. So we can say that 3.8 divided by 0.1 divided by the small box, we're going to have 35 small boxes. So let's count. This is 10, 20, 30. 1, 2, 3, 4, 5. 35 small boxes. That is 3.8. So 35 small boxes will give us 3.8. So when it was 3.8, this is 3.8. When the extension was 3.8, the mass was what? Was 90. So 90 is halfway 80. So this is a 1, 2, 3, 4. 1, 2, 3, 4, 5. This is 90. So you trace 90 and where it intersects with 3.8. That is the point we are going to plot. So this is good. This is 3.8. We're done with that point. So the next point is 4 against this. 4 is right here against 110. 110 is halfway 100. So this is 1, 2, 3, 4, 5. This is 110. You trace it, and where it intersects with 4, that is where you stop. So this is the point. That is the point. The next one is 5.4. How do we locate 5.4 here? Precisely. 5.4 divided by the value for each small box. What do we have? We have 5.4 divided by 0.1. That will give us 54. That is 54 small boxes. So let's count. This is 10, 20, 30, 40, 50. 1, 2, 3, 4. 54 is right here. So this is the same thing with this point is 5.4. 5.4 against 130. 130 is half of 120. So this is 1, 2, 3, 4, 5. This is 130. So you trace this point. Then back to this point. That is the point. The point seems to be off bound. We can't make use of it later. And then the last point is 6.2 as against 150. How to get 6.2 precisely on the graph? 6.2 divided by 0.1. That will give us 62, meaning 62 small boxes. Let's count. This is 10. This is 10, 20, 30, 40, 50, 60. 61, 62. So this is 6.2. 6.2 against 150. 150 is halfway 140. So this is 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. This is 150. So 150, you trade it up there. You use your ruler so that you don't miss at the points. And this is 6.2. 6.2 is here. And then so we are done plotting the points. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the next thing we are going to do is to draw the line of best fits. Is that what I'm doing? I'm gonna place my ruler like this, and my ruler must touch at least 2 points or 3 points. So these 3 points are good points. My ruler is able to capture this point. It's a point here, another point here, one this way, one this side, and one this side. So this is the best line of best fit. I can't go with this. This is wrong. This is also wrong. This is wrong. This is wrong. This is wrong. This is correct. So I can equally go with this also point. This is also correct. I'm capturing 1, 2. This one is even perfectly correct. This with this, or I can choose to go. So let's go with this one. Let's go with this one. So I draw. Good. The next is to find my slope. I will choose this triangle here. You can choose this one. You can choose this one. Your triangle should be very, very big to minimize the error in the experiment. Dot, dot, dot. Dot, 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 dot. Dot, 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 dot. Good. So here is my change in extension, and here is my E2, here is my E1, here is my change in mass, here is my M2, and here is my M1. And so the slope or the gradient of the graph becomes change in E over change in mass. So my E2 is at this point. How do we get up to that point? We say 0.1 times. How do we get this point? 0.1 times 10, 20, 30, 40, 50, 50, 55, 56, 57, 58, 59. 10, 10, 20, 30, 40, 50, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 5. So times 60, and that will give us, that will give us 6. That will give us a what? Let me check it again. That point is actually 6. So write that this is the same thing as E2 minus E1 divided by M2 minus M1. So our slope becomes, this is 6. 6, our E1 is 1. This is 1 minus 1, all in cm divided by our M2. Our M2 is exactly on 120 grams. So write 120 grams minus 20 grams. Sorry, 140 grams. So exactly on 140 grams minus 20 grams. All in grams. You have 5 divided by 105 cm divided by 120 grams. Do that correctly, you have 5 divided by 120. So our slope is 0.0417 grams. Therefore, the slope, let's write it to 0.04167 cm per gram. That is the slope. So we are done with the slope. The next thing the examiners ask us to find is the intercept. The intercept, change in C, is a symbol for the intercept in physics. So how do you find the intercept? The intercept is where the straight line touches the vertical line. So the intercept is directly on this dot here. That is the intercept. So this is a 1, 2. So 2 times 0.1 is the value for the intercept. So write that 0.1 times 2 is 0.2. So the intercept is 0.2 cm. So from the equation y is equals to mx plus c, since the intercept is on the vertical, is on the positive vertical axis, this is the equation for the intercept. For this graph, it is E is equals to k m plus c. This is the equation for this graph. Extension, where k is the slope and m is the horizontal axis and the c is the intercept. So in this case, we'll come back to this later. The next thing they ask us to do here is to determine the difference in the extension x when the mass was increased from 100 to 150 grams. So what we do here is we trace 100, it will touch the line of best fit, and this is it. We trace this point. This is when it was 100. We trace this point. and then find the extension at this point and record it. We call this our E1. So when it was 150 is halfway, which is here, is halfway 140 and 160. We also trace this one to touch this graph at this point. Good. This is 150. Touch it here. What I'm doing is called deduction in physics. Good. Now you trace this point. This is the second extension based on that question. The difference in the extension when it increased from 100 to 150. So this point, okay, let's call this E100. Sorry, E100, and let's call this E150. So the difference in the extension becomes we call it D. Change in the extension becomes what? E150 minus E100. So what is our What is our E100? Our E100 is simply 0.1 times. This is 10, 20, 30, 40, 1, 2 times 42 times 42, and that will give us 4.2. What is our E150? Our E150 is 0.1 times 10 times 10, 20, 30, 40, 50, 60, 1, 2. Sorry, this is 10, 20, 30, 40, 50, 60 times 62 times 62. And that will give us 6.2. So we'll have 6.2 minus that. So we'll have 6.2 minus 4.2. That will give us 2.00 cm. Therefore, the change in the extension when the mass increased from 100 to 150 grams is that. And this is the same thing as X in this particular question. And so they ask us to calculate the period T1 for period T1 and T2. That had been done here already. These are the period T1 and T2 done here already. They also ask us to evaluate, they ask us to evaluate K. Evaluate K is equals to 39.5 X times this X divided by T1 square minus T2 square. Good. So this is very simple. This is the same thing as 39.5 times 2, which is our X, times 2 divided by our T1. Our T1 is 0.4. So we'll have 0.4 square minus 0.3 square. And so our K here from this, as you can see, is given to be 1. From the calculator here, we have 1,128.57 cm negative 2. So the examiners asked us to state Hooke's law, that is 2 marks. Hooke's law states that provided the elastic limit of an elastic material is not exceeded, the extension is directly proportional to the applied force. Mathematically, Hooke's law states that F is proportional to E and F is equals to KE. Watch the video on the theory of Hooke's law and get all that information. To deduce the force constant of the spiral spring from the graph. Deduce the force constant of the spiral spring from the graph. We can deduce the force constant from the graph using this particular equation here. This is given as E is equals to Km minus C plus C. So we can say that our Km is equals to E minus the intercept. So divide both sides by M, so that our K becomes E minus C over M. And this E is the value for, we can get this E from the slope. We can come right here and get our E. 5 is our E. You can choose this 5 to be your E. So in this case, we have K is equals to 5. 5 minus, our intercept is what? 0.2. 5 minus 0.2. Are you following me? Minus 0.2 and G 120, which is mass. Our mass in this case is 120, so right divided by 120 gram, and we have 5 minus 0.2. That will give us 4.8 cm divided by 120 gram. But recall that the unit for the stiffness of the material is from F is equals to KE is equals to F over E is a Newton per meter. So we'll convert everything here to Newton per meter units, so that we divide, we have 4.8 divided by 100, and that will give us 0.048 meters. Yep. Let me be sure of something here. So we divide 120 by 1000 to get it in kilogram, and that results, which is 0.12 times 10 to Newton. That's the force. So that times 10. So we have 0.048 meters divided by 1.2 Newton. So from the we have 0.048 divided by 1.2. So we're having 0.048 divided by 1.2. So meter per Newton. So which is actually an inverse form of this. So we write that 1 all over K is equals to convert this to the original value of K. We write that 1 over K is equals to 0.00 this, so that if we reverse it, we're going to have something like this, that our K is the same thing as 1 divided by 0.004, and that will give us 250 Newton per meter. So 250 Newton per meter is actually the unit for the K. The last question the examiners asked us to look at is to calculate. I wanted to make this video very, very short, but it has become too obvious that this video will be long. The graph becoming longer than the real experiment. This is actually how WAEC questions look like. Watch to the end, I don't skip any part of it. So the last part of this experiment, they asked us to calculate something here. You can see that a spiral spring is compressed by that. Calculate the extension stored in the spring if the force constant is that. If you watch the videos on the calculations, you can actually do that. For what I'm going to do for this video, I will just give you the equation and then I will end this video. This is the same thing as the work done in compressing the spring. The spring was like this, but was compressed to this. So the work done in compressing the spring like this is what they're asking us to calculate. So we have it at that compression, we can liken it to be our extension 0.03 meters. The energy, also known as the work done, that is the elastic potential energy, also known as the work done, is not given if the force constant K is given to be 300 Newton per meter. That is 2 marks. So we have the available equations. W is equals to average force times extension, and that is F all over 2 times extension. We call it equation 1. We can't use this because force is not given. So we'll have the other one. W is equals to KE squared all over 2. We call this equation number 2. So this is the equation we are going to use. With this, you can say that your W is equals to your K, which is 300 times 0.03 all square. You divide that by 2 and you get your answer. You put it in joules. I want to see your answer in the comment box. With this, we have come to the end of this particular video series. Don't forget to subscribe, like, comment, and share. Appreciate my little efforts by promoting physics with Ben in your own little way. God bless you, and bye-bye.